We're going to see now the dielectric in a capacitor. So here we have a parallel plate capacitor, here we have a Q plus and here a Q minus, charge positive, charge negative. A dielectric is usually a isolated or insulator material that is put in between these parallel plates that will increase the charge, the energy that could be stored here. So first, here we have Q plus, Q minus, and this is called Q free because these are positive, these are negative, and the dielectric is neutral. Here it has positive and negative charges, but they are neutral. Because this part is positive, we will induce the negative charge to be here and the positive charge to be here. So this would be Q plus induced and this would be Q negative induced. So we will be talking about Q free and Q induced. The total electric field here, or the net electric field, is the electric field produced by the free charge, the Q free charge, that is just sigma divided by epsilon naught, plus the electric field produced by the induced charges. So let me put first the electric field of free electric field and induced electric field. Now the electric field by the free charges, produced by the free charges, is in this direction, from positive to negative, in this direction. And the electric field of the induced charges is in this direction, is in opposite direction. So actually this electric or induced electric field is in the opposite direction as this, so we usually write it as a negative sign. So the electric field, we know that is for a parallel capacitor is the charge density divided by epsilon naught. So this would be E free, it would be the surface charge density free divided by epsilon naught, and E induced would be the surface charge density here induced divided by epsilon naught. Now we could say that this electric field would be a fraction of this free electric field. So we can say that E induced is, let's say, a constant V times the free electric field. So we have that the net electric field is the free electric field minus V times the electric times the free electric field, or just the free electric field times 1 minus V. Now this could be called 1 over K, or you can think it as K being 1 over 1 minus V. K is the dielectric constant. It's a measure of how strong would be the capacitance then leads to the increase in energy that could be stored. For a vacuum that is approximately air is 1, and we have 8 and 5 for other materials like could be crystal or glass. Anyway, so usually we want a high K. So the electric field, the net electric field would be equal to the free electric field divided by the dielectric constant. In the same way, the charge free density, if we multiply this times some that the same constant V, we get the free surface charge density induced. So again, the surface charge density would be, this the free charge density minus the induced charge density, that is B times the free charge density, and you have the same result, that the net surface charge density is the free charge density divided by K. Or you can say that this, that is the induced, if you have that K is 1 over 1 minus B, or here that 1 minus B is equal to 1 over K, you have that B will be equal to 1 over K minus 1. So you have that the charge induced is equal to the charge free times 1 minus the minus 1 over the dielectric constant, 1 minus 1 over the dielectric constant. And so here you see that if the free charge disappears, so for example if we put together these parallel plates, so there will be no free charges here. So if we disappear the free charges, the charge induced will disappear. Alright. Next, for the voltage, that is the electric field times the distance of separation, the voltage will also decrease by the factor of K, because the electric field decreases with the factor of K. Next, capacitance. That capacitance is area times epsilon naught divided by distance. Here actually we will have an increase in capacitance by a factor of K, because the capacitance is Q divided by voltage. Here we are talking about Q free. The voltage is the electric field times the distance, and the electric field by Gauss law of electricity, we have that the electric field dot the A is equal to the charge inside divided by epsilon naught. So this is also the electric field times the area. So the electric field is equal to the charge inside divided by epsilon naught area. So here we have that the capacitance is equal to Q free divided by the voltage, that is the electric field, that would be the Q inside divided by electric field epsilon naught times area, that this goes to the other way, epsilon naught times area, and here a distance. What's the charge inside? Where is the charge? The charge inside would be this, and this is the surface charge density. So this is equal to the charge times area. Sorry, charge per area. So the charge here. So the charge would be equal to this surface charge density times area. This is the surface charge density. This surface charge density, we have it. Here we have the induced. Here we have the induced put in terms of the free one, and in some part we saw that this is the charge induced, because the area could most of the time be the same. The charge induced is again a factor B of the charge free. So again the Q inside sorry, so again the Q total, Q inside would be again the charge per K, the charge free per K. So here, let me put it here, we have that capacitance is equal to the charge free divided by the voltage, that is Q inside, what Q inside is, where I put it, Q inside is Q free divided by K, and then I multiply this times the distance, and this epsilon naught times area goes here, epsilon naught times area goes here. So I have that the capacitance is epsilon naught times area times the dielectric constant divided by the distance. So the capacitance, this new capacitance is exactly the capacitance that we had before, that is just epsilon naught times area divided by the distance, but now multiplied as this K constant, the dielectric constant. So if we increase the capacitance, the energy that could be stored will increase. Remember that the energy is 1/2 of CV squared. So if we increase the capacitance, we will increase the energy that would be stored. So we want to put a dielectric material that has a very big K, or very big dielectric constant.